All right, the last synthetic section in chapter 19 is section 19.13, conjugate addition. Okay, we're going to see the reverse of the reactivity of alkenes. So with alkenes, we're accustomed to seeing them react. As nucleophiles. In electrophilic addition, be it HBr, Br2, Cl2, the alkene is the nucleophile. And what we're going to see here today is that when we put a carbonyl, so when we have what we call alpha, beta, unsaturated carbonyl derivatives, and I'm going to put a big X here, it can be aldehydes, it can be ketones, it can be esters, it can be amides, a wide variety of substrates have this property. What I want you to see is when we push the arrows to draw the resonance forms that we're accustomed to seeing, now this is a resonance form that might have been similar to what we had drawn for a carbonyl. When we do that, we see that there's a change at the beta position. It's partially positive. Because of this resonance form, we can see that. So we actually have two positions in an alpha-beta unsaturated carbonyl that are partially positive. We already knew that the carbonyl carbon carried a partial positive charge and was electrophilic. The alpha-beta unsaturated compound is also electrophilic and has a partial positive charge at the beta carbon. So these are bidentate electrophiles. Now bidentate, remember dent? I have an appointment with the dentist, my regular appointment in the morning. Dent is for bite. Bi means two. So it has two different places it can act as an electrophile, and a nucleophile can bite into either end of the system. Okay, so this is the key property that we need to recognize. Now the first reactant that we're going to see with these are the amines. In the general reaction, when we have an alpha-beta unsaturated compound, and for these we're mostly dealing with aldehydes and ketones. If we have an amine, and our amine needs to have one hydrogen, we get a product, and by the way, we call this the 1,4 addition. So again, here's our beta carbon, and our amine has added to the beta carbon. Now, how does this occur, and why do we call it a 1,4 addition when it looks like the nitrogen is added there and the hydrogen is added here? Well, this is a bit of a prelude of what's to come soon in the chemistry, and that has to do with the reactivity at the alpha position. So the amine attacks, that pi bond swings up and this one over, and so you see we have 1, 2, 3 arrows there. This will produce an intermediate. Has a proton there and a minus there. This of course has a formal positive charge. Now again, as we've seen before, these proton transfers are not intramolecular. There's a proton loss here and gain here, and this actually makes I don't think you can see that. I'm going to have to move it over here, put it close by. we make this enol form now you've seen the enamine already. This is the ene alcohol, ene and alcohol, the enol, and this undergoes keto-enol tautomerization because the thermodynamically favored form has the proton on the alpha carbon instead of the oxygen. So initially it is a 1, 2, 3, 4, 1, 4 addition. Okay, so these are useful because we make these beta amino carbonyl compounds, beta amino ketones. You've probably heard of alpha amino acids, and so there's a whole field where people look at moving the amino group from the alpha position to the beta position and see how that impacts protein structure, stability, and so forth to understand the fundamentals there. All right, so that's amine addition. Now, there are two more kinds of addition that we want to take a quick look at. The first is cuprate addition. In cuprate addition, we take a diorganocuprate. These are made, by the way, from copper halides plus 2 alkyl lithiums to synthesize them. But these react with carbonyl compounds. I'll just give you a 6-membered ring here as an example. These copper reagents are very selective for the beta position, just as we saw with the amine. So the cuprates are 1,4 selective. All right, so now I've shown you two examples here of this addition. Both of them prefer addition to the beta carbon. Now I said at the beginning this was a bidentate electrophilic system. And so when we react with alkyl lithiums or alkyl Grignards, these have a tendency to add to the carbonyl carbon. So let's take a quick specific example here. If we take this one with either methyl magnesium bromide or with methyl lithium, they add to the carbonyl in what we would call the 1,2 addition product. 1,2 addition. Right, we added to the carbonyl 1,2, 1,2, or 1,2, depending whichever way you want to count it. It doesn't matter there. And both of these give good yields of the 1,2 addition product. So magnesium and lithium, we consider those hard metals and hard Lewis acids, and they lead to 1,2 addition products. The cuprates, copper very far away, it's the other end of the transition metal series. It's almost out of the transition metal series. It's soft and it adds to the beta position. And amines add also to the beta position. All right, so that's a quick overview of conjugate addition. Remember, for all of these reactions, you need to be practicing specific problems and learning to transfer the general information to the specific, like these. Keep practicing.